Welcome to luminescence. So luminescence is the emission of light from an excited state of a molecule. Both fluorescence and phosphorescence are examples of luminescence. So suppose you're standing in a stadium at night with 50,000 people holding lit candles. Now suppose 500 of them, so this is 1%, blow out their candles. Do you think you can notice the difference? This is analogous to a transmittance of 99% or an absorbance of just 0.0044. This is going to be pretty difficult for us to detect. Now suppose that you're standing in the same stadium and there are no candles that are lit. And then 500 people light their candles. Can you notice the difference? This effect is likely far, far more noticeable than the previous effect. And this is analogous to luminescence and explains why luminescence is inherently more sensitive than absorption. With absorption, you're subtracting light, but you already have a lot there. With luminescence, there's none to begin with, or very little, and you're adding to it. And that addition, if you have the same number of photons being supplied through luminescence versus absorbed through absorption, it's going to be far, far easier to detect luminescence, because as a relative amount, that luminescence is far, far more. So absorption is very good for measuring a large number of analyte molecules, whereas luminescence can be used to observe very small numbers of molecules, even down to single analyte molecules. So we've already seen that fluorescence and phosphorescence occur at lower energies or longer wavelengths than absorption does. So if we look at an absorbance spectrum, the absorption spectrum is in black here, and in blue then is the emission spectrum. So the figure below on the next slide shows why emission occurs at lower energy, higher wavelengths, and why the emission spectrum is approximately the mirror image of the absorption spectrum. So during absorption, lambda naught corresponds to the transition from the ground vibrational state of S0, that's here, to the ground vibrational state of S1, so that's there. So that's this transition right there. The peaks in the absorption spectrum, other than lambda 0, lambda naught, correspond to the electronic transition going up to there, plus some quantum of energy going into the vibrational transition. So we're still going from that same state as 0, but now we're going up either to this one, or that one, or this one, or this one, and so on. In polar solvents, solvent-to-analyte interactions usually broaden our vibrational peaks together here so that they blend together into a broader envelope of absorbance. And in less polar and non-polar solvents, the vibrational structure can generally be seen on the electronic transitions. So after absorption, then the molecule undergoes vibrational relaxation down to the vibrational ground state of S1, the electronic excited state. And so that's this level. So no matter how much energy was absorbed, it's all now going down to this level. And then subsequent emission of a photon can occur to any of our vibrational states of our electronic ground state as 0. So we can go from this level down all the way to the ground state, or we can go down to this level or that level, and so on. And these spacings are generally about the same as those spacings, and that means that this spectrum is going to look roughly the same as that one, just mirrored, because here we have energy going in, and each successive energy level that you go up means that more energy was included in the photon. In this case, you have energy coming out of the molecule, and each successive energy level you go up means there's less energy contained in that photon. So the emission spectrum will be approximately the mirror image of the absorption spectrum if the spacing of the vibrational levels here and there is similar, and the probabilities of transitions is similar. So you may have noticed that the lambda naught for the absorption does not exactly overlap here. There's a slight difference there for the emission. So why does that happen? Well, a molecule absorbing radiation is initially in the electronic ground state S0, with a certain geometry and solvation, whichever is the most energetically favorable. The electronic transition is far faster than the vibrational motion of atoms or molecules because it only involves moving an electron, which means, and the electron after all has a mass of at most 1/1800th of the mass of the atom, and that's only going to be true for hydrogen. As you get heavier atoms, then that electron becomes even smaller and smaller mass compared to the mass of the nucleus. And this means that when the radiation is first absorbed, that molecule still has the same geometry and solvation as it did in S0. So, if we look here, we start off with our molecule here, down here in the ground state S0, and it has some geometry and solvation. For formaldehyde, that's a flat molecule. Now we have our energy absorbed in the photon. And initially, right at first, right when that photon is absorbed, the geometry of the molecule is still the same, and whatever solvent molecules are around are still in their same places as well. Then, shortly after that, now the geometry and solvation of the molecule can adjust to the new, most favorable states for the excited electronic state, and this then lowers the energy of the excited molecules from here down to there. And now, when the molecule then fluoresces, from this point back down to the ground state, it returns to its electronic ground state as 0, but now it's still initially, just after the photon is emitted, it's still initially in the S1 geometry and solvation. Now this state, the S0 electronic state, but S1 geometry and solvation, is necessarily higher in energy, less stable than the S0 geometry and solvation. Now how much of a difference in energy there is, that can vary, but this one has to be higher than that. This level has to be higher than that level. And this means that the combination of lowering energy here and lowering energy there means that the emission must occur at a longer wavelength, smaller energy difference between these 2 points as between those 2 points. Because it begins from a lower energy and ends at a higher energy than the ending and starting energies of the absorption transition. So, in a solution, the spectra are broadened because the absorbing or emitting molecules are surrounded by solvent molecules in different orientations. This molecule may have solvent around it in this orientation, and that molecule may have solvent around it in a slightly different orientation, which gives them different energies. And this means that the absorption or emitting molecules have slightly different energies as well. On the other hand, the gas phase molecules are not in close proximity to other molecules, and thus have extremely sharp absorption and emission spectra. So, for simple molecules like water, where we have isotopically labeled O16, O17, and O18 in the water molecule, these can be distinguished by their rotational levels, even though those levels are only 0.2 wave numbers apart. Now the line widths are only 1/10 as wide as that, so this is just how narrow some of these line widths can get if we have the gas phase molecules. So let's look at an emission experiment. So we have over here our light source, we have broad spectrum radiation going into our excitation monochromator. Our monochromator then is selecting one wavelength. We're going to call that lambda EX for excitation, and that light then enters our sample cell via some entrance slit. So down here we've got a blow up of the sample cell, so we have some entrance slit, and we've got our light coming in via that entrance slit. Note that light with wavelength lambda excitation, EX, and irradiance P0 enters. So we've got our P0 there. That's the irradiance of light that's entering that sample cell. Now some of that light is going to get absorbed by the sample, and some of it is going to pass through. And some of that absorbed energy is then emitted as luminescence from our molecule. And note that luminescence must occur at a longer wavelength than our excitation wavelength, which means lower energies. Now that multi-wavelength emitted light, it's leaving our sample via an exit slit, usually at a 90-degree angle with respect to the entrance slit, so the light is coming in here, and that light would go through. So we don't want to put our detector over there, because we would be detecting both the light from the source and the light from our sample. So instead, if we put our detector down here, we're only going to get light that is emitted from our sample. So this multi-wavelength light then goes into our emission monochromator, which selects one wavelength to pass onto the detector. So this is the lambda EM, or emission wavelength. And we can then change the wavelength selected by the emission monochromator to generate an emission spectrum. An emission spectrum is a plot of intensity of light versus emission wavelength. But we can also measure an excitation spectrum by measuring the intensity of light emitted as we vary the excitation wavelength. So at this point then, we're keeping the emission wavelength constant and monitoring that irradiance coming out of the sample as a function of the excitation wavelength going in. So note here that the excitation spectrum appears similar to an absorption spectrum because the greater the absorbance at a wavelength, the more molecules are excited, and thus the more will luminesce. So in emission spectroscopy, we measure the emitted radiation intensity, not the fraction of incident light that reaches the detector, as in absorption spectroscopy. So the detector response varies with wavelength, and that means that the emission spectrum does not accurately reflect the true profile of emitted radiation versus emission wavelength, because a detector isn't responding to different wavelengths with the same efficiency. So if you're performing analytical measurements using a single wavelength, this doesn't really matter. But if you want a true profile, then you must calibrate your detector response at each wavelength of interest. So now let's talk about scattering. Any light that leaves the sample cell via the exit slit and strikes the detector will be recorded in the emission spectrum. But not all of this light is necessarily from luminescence, so it's not necessarily all really signal. If some of the incident excitation radiation is scattered, reflected, or refracted onto the detector, it will be detected just as any emitted light would. So let's compare the emission spectrum of aqueous dichlorofluorescene with that of pure water. So that's what we have over here. Pure water is the black spectrum, so you can see we've got this large peak here at 400 nanometers, and then a smaller peak here, and then another peak there at 800 nanometers. And in the blue curve, that's the fluorescene. Excitation light with a wavelength of 400 nanometers is used to excite our molecules, and then the dichlorofluorescene fluoresces at 522 nanometers, so that's this peak here. But there are three other peaks in both spectra. We see an off-scale peak here at 400 nanometers, we see a small peak here at 462 nanometers, and then a medium-sized peak over here at 800 nanometers. So this strong peak here at 400 nanometers, that's at the excitation wavelength, and that's due to Rayleigh scattering. So the oscillating electromagnetic field of the excitation light causes electrons in the sample, regardless of what atom or molecule they reside in, to oscillate at the same frequency as that 400 nanometer light. These oscillating electrons can then emit that same frequency of radiation in any direction. And naturally, some of this radiation then reaches the detector. So remember that the time required for fluorescence is approximately 10 to the minus 8 to 10 to the minus 4 seconds. Well, the time required for Rayleigh scattering is essentially the period of oscillation of that electromagnetic wave. So that's about 10 to the minus 15 seconds for 400 nanometer light. So because Rayleigh scattering is always present, it's usually filtered out, so it doesn't show up in the emission spectrum. As a side note, you have observed Rayleigh scattering ever since you were a young child, even though you probably didn't know it. So Rayleigh scattering is more effective at shorter wavelengths. Now, shorter wavelengths are the blue-violet end of the spectrum. Longer wavelengths are the red end of the spectrum. So, for example, Rayleigh scattering from 400 nanometer light is about 9 times as intense as that from 700 nanometer light. In other words, blue light is scattered more than the red light is. So, as light from the sun streams through the atmosphere, some of it undergoes Rayleigh scattering, but the blue light is scattered far more often than the red light is, and thus the sky away from the sun appears blue. But then when you're looking at sunset, the sky close to the sun is now scattering a decent fraction of red light, because it doesn't have to scatter it as much to go, let's say the sun is over here, And your eye, if that light ray is going this way and gets scattered, the red won't have to get scattered by as much to get to your eye there. So as the sun approaches the horizon, we get more and more of the red light coming through. And that's why if you see something like this, where you see the sun is down, perhaps just beyond the horizon, but the sky near it is red, because that red light is getting scattered just a little bit to reach your eye, but the sky farther away from the sun is blue, because that blue light is getting scattered far more often. The medium-sized peak in our emission spectrum over here at 800 nanometers, that's this one, is also from Rayleigh scattering. But this is due to an artifact of our monochromator. So a grating monochromator that passes a wavelength lambda will also pass light with integer fractions of the selected wavelength. So at lambda over 2, lambda over 3, lambda over 4, and so on. And note that each subsequent wavelength, so second order, third order, fourth order, and so on, passes the monochromator with lower and lower efficiency. So we're mostly concerned here with this second order one, the lambda over 2. But wait, you might say, doesn't that mean that the excitation monochromator passes 200 nanometer light, 133 nanometer light, 100 nanometer light, and so on? Why do we then see a peak at 800 nanometers? And you're right. But the 800 nanometer peak is not an artifact of the excitation monochromator. It's an artifact of the emission monochromator. When we set the emission monochromator for 800 nanometers, lambda over 2 is 400 nanometers. And that means that some of our 400 nanometer light that was Rayleigh scattered from our sample then passes to the detector. And because the detector is only measuring the intensity of light, not its wavelength, then it appears as though we have 800 nanometer light leaving the sample. So if we filter the 400 nanometer Rayleigh scattered light before the emission monochromator, then this apparent peak at 800 nanometers disappears. And any observed peak at 1200 nanometers, because 1200 nanometers divided by 3 is 400 nanometers, would also disappear as well. Now note that you could filter the 400 nanometer light after the monochromator as well, but you're probably better off for scattering purposes of filtering it as early as you can. So this third peak over here, this really small one, is weak, but it is still observable. And that peak is from Raman scattering. So the energy difference between the 400 nanometer excitation light, this one, and the 462 nanometer light corresponds to a vibrational transition of water. So in Raman scattering, a small fraction of incident light photons give up one quantum of energy for the vibrational transition and are then scattered, and they're emitted in all directions. Those emitted photons have less energy than the excitation photons and thus appear at longer wavelengths. 462 nanometers is the longer wavelength than 400 nanometers. So that's why that peak is there. And that's why it's there in both the fluorescein in water and the dichlorofluorescein in water and the water spectrum. So why are these scattering peaks important? Well, if we shift the excitation wavelength from 400 nanometers to some other wavelength, let's say 410 nanometers, that first order Rayleigh scattering will shift to 410 nanometers. That second order Rayleigh scattering peak over here will shift to 820, because it's got to be double the excitation wavelength. That Raman scattering peak will shift to the wavelength, which is one quantum of vibrational energy less than 410 nanometer light, which would then be 477 nanometers. But our fluorescence peak will not shift, because it doesn't depend upon the excitation wavelength. Now naturally, if you shift the excitation wavelength to such an extent that it's longer than that fluorescence wavelength, we shift that excitation, then no fluorescence is observed because you haven't given the molecule enough energy to undergo that S0 to S1 transition in the first place, and it can't absorb that the energy. So let's take one more look at our emission experiment. Right? So we've got our light source, we've got the monochromator selecting one wavelength of light, it's going into our sample cell. That light emitted, some of the light coming in is being absorbed, some fraction of that is then going to be emitted again. Our emission monochromator is selecting one wavelength and it goes on to the detector. But now we're going to take a closer look here at what's going on in our sample cell. The excitation light is striking our sample with intensity P0, so that's this amount of energy coming in, but light is not collected from the entire sample cell. Instead, light is collected only from this central region, only from that central darker portion there. So we need to be concerned with the intensity of light that makes it to that central region, which is P0 prime. So some amount of light will get absorbed between when it enters the sample and when it reaches that central region. That amount, that light that is absorbed, we don't care about. It still emits light. That region emits light, but we can't collect it on the detector because the exit slit is cutting that out. And note here that P prime is not equal to P0. Sorry, P0 prime isn't equal to P0 because some light will have been absorbed along path B1. So that's this distance here. So only light absorbed in path B2, that's this one, can actually lead to fluorescence that is observable by our detector. That is, the light has to be absorbed in this central region. The light that then makes it to the far side of the central region, over here, with irradiance P prime, is not useful to us. Because any light that passes that central region, if it gets absorbed in the sample or not, it wasn't absorbed, so none of that energy was useful to us, because it can't be used to emit any light. Now the intensity of light that makes it to the central region, P0 prime, is then equal to P0 times 10 to the negative epsilon excitation, B1C, where that epsilon excitation is the molar absorptivity at the excitation wavelength, C is the concentration of the analyte, and B1 is the length of that first section after entering the sample, but before reaching that central region. The irradiance at B2 is then, so this is P prime, is equal to P0 prime times 10 to the negative epsilon excitation, so the molar absorptivity at the excitation wavelength, times the path length of B2 times the concentration. And then the intensity of emitted light, I prime, is proportional to the radiance absorbed in the central region. So this is how much light gets absorbed in the central region. P0 prime, how much light came into the central region, minus P prime, how much light left the central region. If the difference here is 0, then nothing was absorbed, and the intensity is going to be 0 because there was no energy absorbed by the molecules. Okay. K prime here is some proportionality constant. And some of the emitted light is going to be absorbed before leaving the cell, which means that the intensity I that actually leaves the cell, not just that central region, is equal to I prime times 10 to the minus epsilon emission. So this is now the molar absorptivity at the emission wavelength times B3, the path length between the central region of the cell and the edge of the cell, times C, the concentration of the analyte. And we can then combine the previous two equations to get an expression for the emission intensity, which we have here. And we can then substitute our expressions for P prime and P0 prime in to get this. And so now we have a term, we have an equation for the intensity striking the detector is equal to K prime, our proportionality constant, times P0, the amount of energy, the irradiance of light striking the sample cell, entering the sample cell, times the loss of intensity in region 1 before reaching the central region, the absorption in region 2, and a term here for loss of intensity of emitted light in region 3 after leaving that central region and before exiting the sample. So in the limit of low concentration, then each of our exponential terms here are quite small, and this means that 10 to the power of those exponential terms are all close to 1, and this means that we can replace the first term and that last term, the first and third term, with 1. Note that we can't replace that second term with 1 because we're subtracting it from 1, which will then give us 0. Let me go back and show you. So we can replace this term with 1, and we can replace this term with 1, because if concentration is really low, then the absorbance in each of those regions is going to be fairly low. But the absorption in that central region, we can't replace that with 1 because then this value becomes 0. So we can, however, replace that middle term with a power series. So we have 1 minus the epsilon b2c natural log of 10 over 1 factorial, sorry, to the power of 1 over 1 factorial, plus that same epsilon b2c natural log of 10 squared over 2 factorial minus, and so on. But because each term gets successively smaller, we can ignore all the terms after the second, so we're going to keep just these 2 terms. The first term, the 1, and this second term. And all the others get smaller. And that means that the emission intensity at low concentration, we can then plug in, we can replace this term here with a 1, we can replace this term with a 1, we can replace this term here with our power series, so that's in parentheses there. And that means that now we have 1 minus 1, so the 1's go away, and we get rid of the 1 here and there. And now we have this, and so then we can say that the intensity is equal to K times P naught times C, where K has that value, and note here that K is a constant, and that means that emission intensity is proportional to concentration, because K is a constant and P naught is a constant. So emission intensity is proportional to the concentration provided that the concentration is low. So absorption increases more rapidly than emission does, which means that emission will be quenched by self-absorption. So self-absorption is also called the inner filter effect. And at high concentration, the shape of the emission spectrum can change because the absorption and emission both depend upon the wavelength, but they don't necessarily depend by the same amount on the wavelength. And that was luminescence.